Assalamu alaikum dear students. I welcome you to 42nd lecture of probability and stochastic processes. In recent lectures, we have been analyzing Markov chains in terms of their asymptotic or long-term behavior. And in last lecture, we worked with those Markov chains which have a mixture of transient and recurrent states. And to analyze the long-term behavior of these Markov chains, we divided or partitioned the one-step stochastic matrix or one-step transition probability matrix into different regions. There was one submatrix which represented transitions within the group of recurrent classes. And there was another submatrix which represented transitions within the group of transient classes, and there were other two matrices, submatrices in that big stochastic matrix which represented transitions from recurrent to transient or from transient to recurrent classes. And by dividing this stochastic matrix into four parts, we were able to take higher powers of this one-step transition probability matrix to find out the asymptotic behavior or the long-term behavior of the whole chain. And we saw that in the long run, the probability of this Markov chain assuming a value in the group represented by transient classes is 0. So transient classes are visited only finite number of times, and then the Markov chain moves on towards recurrent class and it stays there. Similarly, for the group of recurrent classes, in the long run, there is a stationary probability distribution. This stationary probability distribution can be unique, or it can be a periodic behavior where there are more than one, 2 or 3 or 4 or even more stationary probability distributions which get assigned in a rotating manner. We have covered all these for simple small Markov chains with finite small sample space. Let's quickly review all these ideas for a Markov chain that we have been analyzing, that is a Markov chain of a simple random walk with one end consisting of an absorbing state pair and the other end being a perfectly reflecting end. We'll have a look at its one-step transition probability matrix, its partitions, and the long-term behavior of this Markov chain in terms of the higher powers of these partitioned submatrices. So let's have a quick look again at that Markov chain. On your screen, you can see the graphical representation of this Markov chain. It has two classes. On the right side, there is a recurrent class which has state 0 and 1. And on the left side, there is a transient class which has states 2, 3, and 4. So if you start in any state in transient class, you will eventually move to this recurrent class, and once there, you cannot go back. You will always move within this class. We follow this convention where we assign smaller labels to states in recurrent class and we assign larger labels for states in transient class. By following this convention, when we partition the one-step transition probability matrix, then the elements associated with these classes, the recurrent classes, are on top left, and elements associated with these transient classes are on the lower right. Let's have a look at its one-step transition probability matrix P. This is a 5 by 5 matrix for the Markov chain you just saw, and this 2 by 2 matrix represents the inter-class transitions for recurrent class, and this 3 by 3 matrix represents inter-class transitions of transient class. We will partition this matrix into these 4 submatrices, and this top left submatrix is for recurrent class. This lower right submatrix is for the transient class. These elements on top of this submatrix corresponding to the transient class represents those probabilities which are starting from recurrent class and going into transient class, and they are all zeros, meaning that it's not possible to start from recurrent class and go back to the transient class. And these probabilities are for moving from transient class to recurrent class. We are going to analyze these two submatrices on the top left and this lower right in terms of their long-term stochastic behavior. We know that due to existence of these zeros, if we take higher and higher powers of this matrix, it will have here in top left region higher powers of this, here in lower right region higher powers of this, and these entries will be derived from the entries of these two matrices as well as this matrix, but these entries are going to remain always zero. Let's analyze the behavior of top left matrix, which we call PR. This is a full stochastic matrix of size 2 by 2, because if you add the entries of this submatrix, the row sum is going to give you 1. But this is a substochastic submatrix, because if you add entries, it will give you 1 for the top row, 1 for the middle row, but less than 1, 0.5 for the lower row. So this submatrix corresponding to the transient class is substochastic, and this 2 by 2 matrix corresponding to the recurrent class is fully stochastic. Let's take higher powers of this one-step transition probability matrix to find n-step transition probability matrix and see how this matrix evolves as we take higher and higher powers. Let's look at the 10th power of this matrix. The 10th power of this matrix has all zeros corresponding to these entries, which imply that even in 10 steps, if you are in recurrent state, you cannot move to transient state, which is generally true. If you look at this 3 by 3 submatrix on the lower right, it has non-zero entries, which means that if you start in transient class, in 10 steps, there is still positive probability that you are somewhere in the transient class. And here, these probabilities represents transitions within the recurrent class. Please have a closer look at the location of non-zero entries and location of zero-valued entries in this 3 by 3 submatrix. You can see that there are 4 zeros here and 5 non-zero entries. And have a closer look at the power. It's 10. It's even number. Let's look at the next matrix. This is p raised to power 25, an odd number. Now, the zero values have been replaced by non-zero values, and non-zero values have been replaced with zero values. So this transient class has some kind of periodicity. It appears to be that transient class is periodic, perhaps with periodicity 2. Furthermore, these numbers have gone down, which imply that if you start in a transient state, after 25 steps, probability of being in another transient state is very small. These probabilities range from 3% to 7%. But probabilities of being in recurrent class are higher, and they are going to converge to some value. We can have a feel of the values towards which these transition probabilities are converging to. They appear to be around 0.5. But let's take still higher powers of this stochastic matrix to see where this thing is converging to. So if you take p infinity or very large power, this three columns representing the three transient states have all become zero valued, and these two columns corresponding to the two recurrent states have converged to values of 0.5263 and 0.4737. So this represents a fully stochastic destination matrix of the recurrent class, where final invariant stationary probability distribution for the two states in recurrent class happens to be 0.5263 and 0.4737, and long-term stationary probability distribution corresponding to the three transient states is 0 as expected. We saw that when we are analyzing the asymptotic behavior of a Markov chain which has transient as well as recurrent states, then we can partition this Markov chain into two groups. One group represents transient states, other group represents recurrent states. Similarly, we can partition the one-step transition probability matrix into four submatrices. And if we have put small labels to states in recurrent class, then the top left submatrix represents interstate transitions from states in recurrent class to states in recurrent class, and lower right submatrix represents interclass transitions when classes are the source class as well as destination class in recurrent group. So by taking the higher and higher powers of this one-step transition probability matrix, which has a partition associated with it, we saw that the submatrix representing interstate transitions for transient class converges to a matrix which has all entries 0. And the submatrix corresponding to the recurrent class converges to a destination matrix which represents stationary probability distribution for the states in recurrent class. We can have another view on this submatrix representing the recurrent class and the submatrix representing the transient class, and we can analyze these submatrices individually using eigenvalues and eigenvectors to have their asymptotic behavior analyzed separately. Let's start with the analysis of top left submatrix representing the recurrent class. The 2x2 top left submatrix corresponding to these two states 0 and 1 represents this recurrent class, and for this class all intra-class transitions are shown here with probabilities of 0.1, 0.9 and 1. If we take this 2x2 submatrix for all these transitions within this class, we can analyze its asymptotic behavior using eigenvalues and eigenvectors. Here is the 2x2 submatrix PR, and probability of moving from state 0 to state 0 is 0.1, and other probabilities have other meanings associated with that. If you take this fully stochastic submatrix and find its eigenvalues and eigenvectors, you see that eigenvalues are 1 and minus 0.9, and corresponding eigenvectors are 0.5263 and 0.4737. This eigenvector, horizontal row, top row, is associated with this eigenvalue of 1, and this eigenvector of minus 0.5, 0.5 is associated with this eigenvalue of minus 0.9. I hope you have a clear vision where this matrix is going to lead us to. If you take higher and higher powers of PR, then using the diagonalization principle, you will end up with 1, 0, 0 and 0 here, because higher and higher powers of this eigenvalue are going to converge to 0. So if you take the higher powers of PR through this diagonalization process, you are going to have these two rows same as this eigenvector. So this eigenvector represents stationary probability distribution for these two states 0 and 1, which comprise the recurrent class. So these two values of stationary probability distribution are also shown in this P infinity, where the same values appear corresponding to states 0 and 1, and all other entries are 0. Let's analyze the submatrix corresponding to these three transient states 2, 3, and 4. So the submatrix corresponding to all the transitions within this class is going to be a 3 by 3 matrix, and we call it Q. Here I have shown the Q, and you can see that the sum of rows is not 1 for all the rows. And if we just diagonalize this 3 by 3 matrix, the eigenvalues are 0.9, minus 0.9, and 0. And you have sufficient background to visualize where the higher powers of this Q are going to be. Because of these eigenvalues with magnitude less than 1, this matrix is going to converge to 0, 0, 0, and the higher powers of Q, the matrix representing transitions within the transient class, is going to converge to all zero-valued matrix. And you can confirm that within this P infinity that this 3 by 3 submatrix represents the destination matrix for higher and higher powers of this matrix Q. We have analyzed the asymptotic behavior of Markov chains with transient as well as recurrent states using eigenvalues and eigenvectors of submatrices corresponding to the two groups, the transient and the recurrent group. And the result is the same, that in the long run, probability of Markov chain visiting any transient state converges to 0, and probability of Markov chain visiting a recurrent state depends upon other things, like how many other recurrent states are in the group representing the recurrent class, and whether there is a periodicity in that recurrent class or not. The bottom line is that if we start in a transient state, then we visit this transient state or other transient states only finitely often, and after that the Markov chain evolves and attains a recurrent state and never comes back to the transient state. So in the long run, the Markov chain is going to be found in one of the recurrent states and not in any of the transient states. But the question is, what happens before this long run, before this asymptotic behavior? If we start in a transient state, what happens before we actually get absorbed in one of the recurrent groups? To analyze this transient behavior, the behavior before we get absorbed in a recurrent state, we need to talk in terms of averages, because this transient behavior is an unpredictable behavior. It is not like the stationary probability distribution. Here, if we start from a transient state, it's possible to move and get absorbed in the recurrent state in fewer, like 10 or 15 steps, or it's possible to continue to stay in the transient group for 25, 30, or even more sampling instances before we get absorbed. So you have to talk in terms of averages. So let's start the analysis of the transient behavior of Markov chains, the behavior before we get absorbed in a recurrent state and then stay there. The first concept that we need for transient analysis of a Markov chain is the concept of indicator function. An indicator function is a random variable, or you can say it is a transformed random variable. It is a random variable defined on the underlying random variable taking on a particular value. So if underlying random variable is xm, that is the Markov chain random variable at mth sampling instance. And then we are interested in this fact whether at mth sampling instance the Markov chain is in state j or not. We are only concerned in a particular state j and a particular random variable xm, and there are only two possibilities. Either this random variable has assumed the value j or it has not. So if it has assumed value j, we assign a value of 1 to this random variable, the indicator function. So indicator function for this event, xm being in state j, is 1, and indicator function, the value of this transformed random variable, if xm is not in state j, is 0. So this is a derived random variable defined in terms of an underlying random variable xm and the fact whether it is in a certain state j or not. Please note that this whole expression inside these curly braces is just an identifier. The values are either 1 or 0. This is just an identifier saying what is the underlying event to which this indicator function is being assigned to. So if this indicator function is a random variable, it must have an associated probability distribution function, or in this case probability mass function, because it has only two values, 0 and 1. So there will be some probability associated with 0 and some probability associated with 1. We are going to analyze this probability later on. One thing that you should observe is that this probability distribution depends on the starting state of Markov chain. If we start in state 0, then probability distribution associated with this particular event or this indicator function will be different compared to the probability distribution if we started in any other state, say 1 or 2. We are going to use this fact that indicator function has a probability distribution that depends on the starting state in next few minutes. The next concept that we are going to use for transient analysis of Markov chain is number of visits to a state. So if we take a certain state j and let the Markov chain evolve and count the number of times this evolving sequence of random variables take on the value j, and that is called the number of visits. And if you continue to observe Markov chain, then we may have more and more visits. If the state is transient, then these visits will be finite, and afterwards, even if we let the Markov chain evolve, there will be no more visits to that transient state. And if that state is a recurrent state, and if we let the Markov chain evolve, then there will be more and more visits to that recurrent state. We'll start this transient analysis of number of visits by limiting our observation window. We'll start our observations at sampling instance 0 and stop at sampling instance n. So during the first n plus 1 sampling instances, we will count the number of visits to a certain state j. And of course, this is going to be a random variable, quite a complicated random variable, a derived random variable derived from all the underlying random variables in the Markov chain. Since we are going to count the number of visits to a certain state j, we should use indicator function, because indicator function is also a derived random variable with an underlying random variable which is member of the Markov chain, and this indicator function, the derived random variable, has value 1 if that underlying random variable assumes the value of interest j, and it has value of 0 if it does not assume that value j. So we'll think of all the underlying random variables which are in the Markov chain. On top of that, there are indicator functions telling us if a certain random variable has assumed a certain state j, and on top of that, we are going to count the number of visits, the number of indicator functions which have values of 1. So there is a 3-layer derived random variable stack which we are going to use to find the number of visits to a particular state j during the first n plus 1 observations. We are going to represent this number of visits to state j up to sampling instance n with y. So capital Y with 2 parameters j and n represents number of visits to state j up to sampling instance n. And it is obvious that this random variable y, j comma n is nothing but sum of all indicator functions xm is equal to j, where m varies from 0 to n. So this summation gives us number of visits during the sampling interval which start at 0 and end at n. This random variable will also have a probability mass function associated with its behavior, and this probability mass function also depends on the starting probability distribution. I'll give you a simple example. Suppose you limit this n to 0. So you are just observing the random variables for the first sampling instance. And then what is the number of visits to a certain state j? It depends what is the starting probability. If we start in state j, then this is not a random variable at all. It's a deterministic quantity and it is 1. And if we start in any other state, then at starting point, the probability of visiting this state is 0. Let's extend this argument. Let's stop at 1. So we are going to observe the number of visits to certain state in first two sampling instances 0 and 1, and we are going to count the number of visits to a certain state. Let's say if we start in state j, then for sure the number of visits to that state is 1 or more, and the number of visits to other states if we start in state j depend upon the one-step transition probabilities. If the one-step transition probabilities can take us to the state in question, then we'll have probability of more than 0 of having visited that state. And if you take large values of n, then the associated probability mass function will be quite complicated. But with this convention of indicator function, we can certainly find the value of this number of visits in sampling instances from 0 to n more easily. As I said, the probability mass function of this y, j comma n depends upon the starting probability, because the probability of this indicator function depends on the starting probability distribution. So we are going to find different derived quantities in terms of these two random variables, the indicator function and number of visits. And we know that these quantities depend upon the starting probability distribution. Let's first look at the conditional probability of this indicator function of xm being in state j. And we are going to condition it on the starting probability of x0 being in I state. So if we know that x0 was in I state, that is the conditioning event, then probability of xm being in j state is nothing but the I comma j value of pm, or the m step transition probability matrix. We know where we were at time 0, and we want to find the probability of being in state j at sampling instance m. Then probability of jumping from state I to state j in m steps is I comma j entry of pm. We can use this fact and this conditional probability to find the expected value of number of visits to state j in first n plus 1 sampling instances, given that we start at sampling instance 0 in state I. And we are going to use this for expected value of this. The expected value of this random variable y, j comma n, or number of visits to state j in first n plus 1 sampling instances, is a summation over all possible values that this random variable is going to take and associated probabilities. Since we are counting number of visits to a certain state j conditioned on a starting event that we start in state I, we have to only consider those instances where the state is visited or those instances where the corresponding indicator function assumes a value of 1. And if the corresponding indicator function assumes a value of 1, then associated probability is Pmi, j. So we start with sampling instance 0, go all the way to sampling instance n, and during this process, if any of the random variables x0, x1, x2 indicator here with xm assumes the value j, then we know that the corresponding indicator function has value of 1, and we multiply the associated probability and sum this all up. Since the associated event has a value 1, we can just simply replace 1 for all these indicator functions and get the expected value of number of visits to state j starting from state I at sampling instance 0 and stopping our observation at sampling instance n to be summation from m0 to n of I, j values of all these m step transition probability matrices where m varies from 0 to n. So number of visits to a particular state in the average sense, that is the expected value of number of visits to a particular state conditioned on the fact that we start in another known state, can be obtained by a summation, and that summation is for sum of I, j values of m step transition probability matrices. So if you want to count the number of visits to state j in first 100 sampling instances, then you take summation from 0 to 99 for all n step transition probability matrices where n varies from 0 to 99. Let's have a look at implications of this summation and how we can use this to find the average expected number of visits to a certain state with known starting state. So in general, if we want to find the number of visits to state j up to sampling instance n, given that we started in state I, then we have to find the I, j entry of this matrix, which is sum of these n plus 1 matrices. I is identity matrix, P is one-step transition probability matrix, P with index 2 is two-step transition probability matrix, and lastly Pn is n-step transition probability matrix. We know how to obtain these n-step transition probability matrices by taking higher powers of one-step transition probability matrix. Hence, this is equivalent to I, j entry of I plus p square plus all the way to p raised to power n. This holds in general. If we are looking at the number of visits up to sampling instance n inside a recurrent class, we start in a state which belongs to recurrent class and we remain in recurrent class, because once you are in a recurrent class, you cannot go back to a transient class. Hence, if you start with state I, which is in recurrent class, the state j must be in recurrent class. So if two classes I, j are both in the recurrent class, then this expected number of visits in first n plus 1 sampling instances comes out to be I, j entry of this matrix, which is I, the identity matrix, plus PR, the submatrix representing the recurrent class and its higher powers. Similarly, if we have two states that are in transient class, then we can have this formula representing the number of states, the number of visits to a certain state j starting with state I. And if we move from a transient state to a recurrent state, you cannot use this formula. You have to use this top formula, which has the general expression for the whole one-step transition probability matrix of the whole Markov chain. But if you limit your visits from recurrent class to recurrent class, you can use this. And if you limit your visits from transient class to transient class, you can use this bottom formula to find the expected number of visits to a certain state j, starting with a certain state I. Now the question is, what happens in the long run? What happens to expected number of visits to a certain state in the long run? We know that if that state is a recurrent state, then we are going to have infinite number of visits to that state in the long run. And you can have this as extension of the previous formula, where we used I plus PR square and so on, and you continue to take higher and higher powers of this matrix PR and keep on adding all these matrices and then looking at the I comma j entry of this summoned matrix. So the long-term number of visits to a recurrent state are being shown here in the formula as a limit. So this is limit n goes to infinity I comma j entry of this result, which is sum of all these powers of PR. If you know that higher and higher powers of PR will have non-zero entries representing the stationary probability distribution, and if you take an infinite sum of these matrices, all of them having non-zero entries, you will have its I comma j entry being converging to infinity, or you can say diverging to infinity. Hence, if we have a recurrent state, the long-term number of visits diverge to infinity. But the question is, what is the fraction of times that state is visited? If we are looking at a large value of sampling instance, then how many times out of these sampling instances that state was visited? And you know we are talking about a long-term fraction of that state being assumed, and that is nothing but its long-term stationary probability distribution. So if we divide the number of visits to state j with the total number of sampling instances, then we are going to converge to pi j, and this pi j does not matter where we start. We can start at any state and we will have this number converging to pi j, or the stationary probability distribution value associated with state j. Similarly, if we have a transient state, then the number of visits in the long run can be found by taking the limit of this summation of all these matrices 1, which is I, Q, Q square, Q cube, and so on. We know that if Q represents the transition probability matrix for all states within the transient class, then higher and higher powers of Q is going to give us a matrix with all entries being 0. Hence, after a finite power, all further powers of Q will give 0 valued matrix, and hence the summation of all these matrices before that is going to give us a matrix with finite entries. Hence, the I comma j entry of this infinite summation in the limit is going to give us a finite number less than infinity. But if you have this finite number and take this limit, that is the fraction of time in the long run that a transient state is visited, then that number is going to be 0, because we know a transient state is only visited finite many time, and hence if you divide it with n and take this limit, you are going to have 0. So fraction of time a transient state is visited in the long term is 0, and number of times it is visited before Markov chain gets absorbed in a recurrent class is less than infinity, a finite number. Now let's try to find those numbers for states in transient class. So if we want to find the average number of times a transient state J is visited when we start in a transient state I, that is I comma j entry of this matrix, which is result of summation of an infinite number of matrices I plus q square plus q cube and all the way towards infinity. State I has to be a transient state, because if it is a recurrent state you cannot come back to a transient state, and state J is also a transient state, and we want to find out the average number of visits when n, the sampling instance, goes towards infinity. We are going to simplify this infinite summation by multiplying this infinite summation with I minus q and dividing it with I minus q. This multiplication of I minus q and division with I minus q is a trick that we learned in FSC or A level, where we wanted to find the summation of a geometric series. And in a geometric series, things are also like that, 1 plus r square plus r cube. So there we multiplied the result with r and subtracted that. This is exactly the same thing. I have written I minus q on the numerator and I minus q on the denominator without affecting the expression. And now I'm going to simplify the numerator. So if we simplify the numerator, you multiply I with I, you get I. You multiply I with minus q, you get minus q. But this I into q is going to give you plus q. Hence, they are going to cancel out. If you cancel out all these terms, you are eventually going to end up with just I. Hence, this expression is equal to I divided by I minus q, or I minus q inverse. So, if we continue to observe the Markov chain for infinite time and count the number of visits to a transient state, then on average, that number is going to be I comma j entry of this matrix I minus q whole inverse. Now the question is, can we actually find this inverse of I minus q? Is this matrix invertible? The answer is yes, because the matrix Q, the submatrix, has all eigenvalues with magnitudes less than 1. And this I, the identity matrix, has all eigenvalues with magnitude 1, or actually 1. So if you take the subtraction, then all eigenvalues of I minus q are going to have amplitudes which are going to be non-zero, because none of the eigenvalues of q is 1. You take subtraction, none of the eigenvalues of I minus q is going to be 0. Hence, this I minus q is definitely invertible. Now we will take a few examples of Markov chains with some transient classes and take inverse of this I minus q to say something about average number of visits to these transient states before the Markov chain evolves in such a way that it gets absorbed in a recurrent class. Let's have a look at the first example. Here I'm going to take the example of that random walk with one end consisting of two absorbing states, or a group of absorbing states, a recurrent state. So we are going to find the average number of times these states are visited before the Markov chain moves into this group and never comes back. So what we need to do, we need to find the inverse of I minus q, where q is the transition probability matrix for states 2, 3 and 4. Here, this is the q we are talking about, the lower right submatrix corresponding to 3 transient states 2, 3 and 4. If you take this q and find I minus q, it will have these values. And if you find its inverse, then it will have these numbers 4, 5, 2, 3, 5, 2, 1.5 and 2.5. It's quite meaningful to talk about 2.5 visits to a state before the Markov chain gets absorbed, because we are talking about average number. It means sometimes it's going to be 2 visits, sometimes it's going to be 3 visits. Actually, it's possible to have 4 or 5 visits. The 2.5 just represents the average value of number of visits to this class, this state where this 2.5 appears. Let's write this small I minus q inverse matrix next to the graphical model of the Markov chain and see how we can interpret these numbers. So this number at top left corner of I minus q whole inverse represents average number of visits to state 2, the first of the transient states, when we start in state 2. So if we start in state 2, then average number of visits that this state is going to get before it gets absorbed here is 4. And if we start at 2, then average number of time state 3 is visited before this Markov chain gets absorbed here is 5. Similarly, the average number of visits to this state 4 when we start here is only 2, which makes sense because if we start in state 2 and you visit state 4, then chances of ever coming back to again to state 4 is small, because once you are in state 4, you are quite likely to get absorbed here. Let's look at the next row. So if we start in state 3, then average number of visits to state 3 is shown here, which is 5. And once again, average number of visits to state 4 before getting absorbed is 2, and average number of visits to state 2 before getting absorbed is 3, which is less than 4, because now you are closer to getting absorbed, and moving back to state 2 more number of times is less likely. Similarly, if we start in state 4, then average number of visits to state 4 before getting absorbed is only 2, including the visit where we started, the visit at state 0. So on average, if we start here, then we come and visit it again only once before getting absorbed. And similarly, if we start in state 4, then average number of times that we visit this far away state 2 before getting absorbed is even less. It is 1.5. In today's lecture, we extended our asymptotic analysis of Markov chains with transient and recurrent states. We also started talking about the transient behavior, and we started the transient analysis of transient states, that is, the behavior of these states before the long-term behavior where they get absorbed in the recurrent group. In next lecture, we are going to finish this analysis of transient states in terms of average number of visits before absorption, and then we are going to continue with the analysis of recurrent states in terms of these concepts of number of visits. Till then, I wish you the best. Thank you. Khuda Hafiz.